This is our first module on policies. Module 1 is on policy function approximations. So examples of PFAs. A PFA is any analytical function that translates information in a state variable to a decision. It is the only one of the 4 classes of policies that does not involve an embedded optimization problem. It may include lookup tables, linear and nonlinear functions, nonparametric functions, and deep neural networks, any function that might be used in machine learning. For example, some of the most popular classes are linear decision rules. These are linear models. So in process control, we might have a linear combination of features that depend on what we know. That's the state variable. So we can take whatever information from the state variable and cherry pick features. For example, in an inventory control problem, we might have a state of here's the inventory and here's the price. And we might construct a series of features starting with a constant 1. The inventory squared, the price, the log of price, the product of resource times the price, spin that out into a linear function, and that could be a policy. We just have to tune the parameters theta. A PID controller is very well known in optimal control. This arises in applications of like temperature control when we're trying to control the temperature in a room or a furnace or an oven, flow control of liquids and gases, level control in tanks and reservoirs, administering drugs like insulin to control blood sugar. So we compute 3 variables. First is the error between the target value R that we're trying to achieve and the Y value that we actually observe. We'd like the 2 of those to be equal, and the difference is our error. Then we can do the sum of the errors. That's the integral. We do a cumulative sum. TS is the length of the time interval. And so if we multiply the time interval times the error, that's the error times time and sum that. And then the differences in the errors would be a derivative. So we have the error, the sum of errors, and the derivative. We pull those together into a linear function where each of these terms has a linear constant. What the PID controllers are used for is when we're trying to hit a target, we don't want to overshoot, we don't want to undershoot, we don't want to oscillate. Randomized policies or parameterized policies. Epsilon greedy is a popular policy in reinforcement learning, especially in games, where with probability theta we may do what appears to be best, or with probability 1 minus theta we may just choose a step at random, and that's in order to force exploration. A little bit more elegant way of forcing exploration is with what's called a Boltzmann policy, where what we'll say is, let's say the value of an action is some function c that depends on the state in the action. Multiply that times theta, put it in an exponential, divide that by the sum of those terms over all actions. That's a probability. Now, if theta is equal to 0, you're going to do any action with equal probability. As theta gets bigger, you're going to do the action with the highest apparent reward with the highest probability. And so that allows us to focus on the actions that appear to be best while still encouraging some exploration. Here's a battery arbitrage problem: when to charge, when to discharge. I want to pull energy from the grid when the prices are low, sell it back when the prices are high. I'm going to do that with a simple formula. This is, again, another form of PFA. It's a step function. And you can see in the graph below, when the energy in storage it's normally at capacity, but every time there's a spike in price, I'm going to sell back to the grid and get that price. I have 2 tunable parameters that I have to tune. Here's another example of a little bit more complicated energy storage problem. This was an actual application done by a Brazilian postdoc who worked in my lab for a while. Now, he came up with this function purely by common sense, and this is not unusual. PID controllers are also a certain form of common sense. It's just, there's a natural structure of the problem. Once again, this policy only has 2 tunable parameters, but the control of all the flows between the various sources and sinks of energy are just done by common sense. Here's a problem, inventory management at Amazon. They decided to use a deep neural network. And what we're going to do here is the variable S, that's the state variable. Now, in inventory problems, we tend to think of the state as the inventory, or maybe there's a price. At Amazon, what they did was they took any relevant information, including information that would have been used in a forecasting routine. Now, they didn't explicitly do forecasting. What they did was to say, oh, well, let's take the history that we would use in forecasting and any other economic information. This is where you just throw whatever you have into the neural network. X there is the neural network. It's a very large one. On the left-hand side, you have every possible input, any piece of data that you think might be relevant. Now, we're not going to plan just one inventory. Maybe we're going to do 50,000 different items. So that would be 50,000 different outputs. Their first test was with 10,000 items. This model had about 10 million to 100 million parameters. Beautiful thing about neural networks is you can differentiate them. There's standard software that will take the derivative of this neural network with respect to theta. And what they'll do is they'll just put this in a simulator, run it over historical data, and tune the thetas until they get the best possible response. This is a classic PFA, just a modern one using deep neural networks. So I like to build a bridge sometimes between machine learning and sequential decision problems. In machine learning, we're searching over functions. And in sequential decisions, we're also searching over functions. The functions are called policies, but they're still just functions. In machine learning, we're going to use a training data set. In sequential decisions, say as with the Amazon problem, we model the dynamics of the problem and the objective function. So there was no training data to say, here's the decision, build this function to match the decision. We tuned it so that it just produced the best possible performance. Now, policy function approximations represent any possible function that we might use in machine learning. So you could go hire somebody with a really strong background in machine learning, bring them over, and the only difference here is that you're not going to use a training data set. You are going to code up a model of the problem. And so you need that. Now, policy evaluation, there are three ways to evaluate a policy. Amazon used historical data. People in finance often do this. They'll take history of prices as long as they're not affected by decisions. You could also do learning in the field. That's online learning, where I'm saying I'm going to take a problem where I actually observe what's happening. So it takes a day to observe a day. It's very slow, but I don't have to do any modeling. And if it's the case where my decision making affects the exogenous information, then that's okay. Then I that's all naturally built in. I observe it. The price you pay is that it's very slow. So the last way is the way where you say, okay, I'm going to have to build an underlying stochastic model so that I can build simulations of all the random information. And this seems like a natural process. It can be very hard. The problem is correlations. You can have correlations over time. You can have correlations between different information processes. This can require some fairly sophisticated mathematics, but if you can build such a model, then it allows you to do simulations, even if the decisions have an impact on the exogenous information. You can do lots of simulations and capture that impact. So evaluating policies is hard. Online policy evaluation, as I said, is very slow. I call this learning while doing. I have a short video at tinyurl.com/learning while doing. It's a video of a situation of optimizing the cash held on hand for a mutual fund. It's a very simple policy. I'm developing this as a game. If you go to the STA website, warrenpowell.org, go to teaching materials and then click on games, you'll see a work in progress where you can play the cash holding game. Or you can do offline simulations. Offline simulations can be very noisy, often are very noisy, and can be computationally very demanding. As an academic, we would always do offline simulations because learning in the field is too slow, and it's hard to do some types of experiments. Okay, more on policy function approximations on the SDA website. Go to policies and then just click on policy function approximations.